10.4 radius of convergence. So we did this earlier, and I pointed out that we're going to come back to it. And the funny part is this isn't even the end of it. We're going to talk about the endpoints of the radius convergence in the next lesson. So a series that converges means it's a number. We might not even know what number. We just might know that it's going to be some number, which is a really strange thing. But hey, this is math. What'd you expect? This is not a number. It just keeps getting bigger and bigger, or smaller and smaller, more negative, more negative. So one of the moments of clarity I do try to bring to students is right here. What does the following equal signs mean? Because you're like, oh, they're equal. It's obvious. Something plus something equals something. That's obvious. And this would just be the equity or equality of, some real numbers. All right, here's another equal sign. Well, this is not real numbers. This is just, we'll call it the equity or equality of expressions. These are equivalent expressions because any number I put in here for x works. Notice on the first one, I don't even have an x. Got my little OCD here, quality. That's horrible. Over here, it's really more of an open sentence. It's a question. What's going on here? Well, it's an equation. So it's really an open sentence. You might be able to finish a sentence, you might not. In this case, there's two answers. 2 and -2 would both work in there. Right? But what if we had x squared equals -4? Well, there's no solution. Oh, unless we go into the imaginary world. In that case, we got all sorts of complexity here, right? So this is an identity, and you would say, yeah, it works for everything. No, it doesn't. I can't put -1 in here. And this is just if I go x plus 1, x minus 1 over x plus 1, cancel, cancel, I'm left with x minus 1. So we would say this is an identity, but it's got conditions. For this one, x cannot equal 1. 1 or -1, -1. So that's where we're going with this. We are working in this fourth range here, because we'll look at things and say, well, they're obviously the same. I'd avoid that word obvious. All right, here's a geometric with a0 equals 1 and r is -x squared. So we can write it as first term, then multiply by -x squared. We get a general term here, assuming we start at 0. So this would be sum from n equals 0 to infinity of -1 to the n, x to the 2n. Important we're clear about where we start. For us, the AP exam doesn't care quite as much, but for us, it's nice to know. So does it work no matter what I put in here? No, it does not. It only works when the r value, in this case, -x squared, absolute value of that is less than 1. So we have to find the condition. And for series, we're looking for what's called the interval of convergence, which I will abbreviate everywhere I can, the IOC. When does it work? Well, that's what this tells us. All right, so -x squared has to be less than 1. It's going to be an absolute value, so it's going to be basically x squared has to be less than 1. square root. And we find out that we get absolute value of x is less than 1. It's the same thing, square root absolute value is this. All right, so it looks like the IOC, -1 less than x less than 1. The radius of convergence, because there's a center to this. By the way, I picked a horrible example with this negative x squared. We'll call that ROC, is 1. Find the center, 0, and how far do we go left and right? 1 that way, 1 that way. This isn't even all of it. This is most of it. We might have some equals here. We're going to have to check. That's 10.5. We'll talk about the endpoints. And of course, oops, sorry about that. We'll check. That's in 10.5. And of course, that's not the only thing we'll do in 10.5. There's always dozens of things going on just to keep everybody on their toes. All right, what's next? So lots and lots and lots and lots of writing here. Convergence theory, theorem for power series. 3 possibilities with respect to convergence. All right. If it converges. So, hey, it's going to converge. Great. So there's some positive number r, such a series diverges. Remember, we just did centered at 0. X minus a is greater than r. But diverges when it's greater than r. Converges when it's less than r. All right. So you end up with between a minus r and a plus r, like we just did. Sometimes it converges everywhere. R equals infinity. R sine, cosine, and tangent, arctangent. No, sine, cosine, and e to the x converge everywhere because we have factorials on the bottom. Or sometimes it converges at one number and it's got a 0 radius. Let me fix that from the previous page. We would not say ROC, we would say radius equals 1. Apologies. All right, so got all these tests we're going to throw at you now. It's annoying. So what do? How do we test? How do we check? The Nth Term Test is one that you have to have going in, and most people forget about it. Does the limit of the sequence go to 0? All right, it's got to go to 0. So, I mean, if we're also oscillating, it diverges. Doesn't go to 0. All right, we're adding things up. We can't be adding 1 and -1 at the end. We have to add 0 at the end. And it just has to be eventually getting to 0. It might be bouncing around and doing this, and then eventually it gets to 0. So that's number 1. Hey, this is something that gets used rarely, but I've seen it used in an AP test. Hey, does this thing diverge? Why not? Converge or diverge? Why doesn't it converge? Well, the terms aren't going to 0. Done. And by the way, almost everything we do is, if it does this, that means it diverges. All right, but it doesn't necessarily mean it converges, and back and forth we go. The direct comparison test, which, if I'm not mistaken, I toss this out in terms of doing an example. We're always going to compare to e to the x. It's just the way it always seems to work. Always compare to e to the x. And it would just mean that, do I have an example here? I hope not. I have an example. It just means that compared to the one with factorial on the bottom, we know this is going to work. I've never used this. I have used this, but I always have a better choice. So prove that this converges. Well, x to the 2n over n factorial squared, it's going to be smaller because this is going to get freakishly big. And this is over the long term, maybe not each term, but over the long term. That's going to be less than x to the 2n over n factorial, because if we square it, it gets freakishly big, which is equal to x squared to the n over n factorial. And that's just e with x squared in. So that's e to the x squared. And we happen to know that converges. no matter what we put in for x. Notice in this, we don't get into that whole interval of convergence nonsense. Yeah, okay. And also notice in the previous definition, we got into something about non-negative terms. What's that all about? Well, we're going to get an alternating series soon, so just hang on and trust me for now. So here we go. Now we get into the alternating series. If the series converges, all right, the absolute value converges, then it converges absolutely. In a little bit, we're going to have things that only converge because they alternate. What? What's going on? I don't know. Yeah, you're going to have to wait till I do like a zillion examples. But if it only converges because of the alternating aspect, then we say it converges conditionally, right? So absolute convergence means it converges, like whatever. Show that this converges for all x. I don't even want to get into this because we'll do this kind of absolute value thing. Basically, since this goes between 1 and -1, it's smaller than that. And that is more or less e x to the 0. So we know it converges. All right, I considered cutting all this out of my notes, but I didn't because there's enough in here that you need to have the groundwork for when we get later on. So my point is, don't panic. All right, we're always going to convert. What did I say? We're always going to compare it to e. You see factorial on the bottom, is you can just write, because it's less than e, it converges. Right? Very rare, very rare. All right, this is the one you need to know. This is the one we're going to use all the time. And it's bizarre. The first few times you use it, you're like totally lost because I have 3 different things that are going to go on in the next problem, and you're going to get lost somewhere in it. So, all right, here's a ratio test. We take a term, the next term, divided over by this term, and we get some L. If it's less than 1, series converges. If it's greater than 1, it diverges. And then, like I said, a ton of these are inconclusive, and go do another test if it equals 1. So now we get to radius convergence, and we use the ratio test to find it. So whenever they're asking for radius of convergence, you're going to do the ratio test. Here we go. Limit as n approaches infinity. Now we add 1 to each thing. Now we're going to divide, and I'll do this just this one time, by the previous term. Which, of course, we do that whole flippy thing. This is going to go on the bottom. I'm going to put it with it because I'm going to look at these two together. Notice they flip differently. Here I've got n plus 1 over n, and here I've got 10 to the n over 10 to the n plus 1. All right, n goes to infinity. This is, if I use L'Hopital's rule, infinity over infinity, derivative 1 over 1, this is 1. This, we do a little magic algebra, see ya is just x. Same deal here, see ya is just 10. We get absolute value of x over 10. I almost always forget my absolute value. But what we just find out is, hey, I don't know what x is. But according to this up here, if it's less than 1, if that whole thing we just did is less than 1, it works. So we say, yes, it works, but only when the absolute value of x over 10 is less than 1. Absolute value of x is less than 10. Negative 10 less than x less than 10, r equals 10. centered at 0, 10 both ways. That's the radius. At this moment in time, if I'm watching this video, I pause it, rewind it, watch that again. At the same time, we're going to do 7,000 or 8,000 examples like this. Just kidding, it's 2 or 3, of course. So let's get going. Limit n approaches infinity. N plus 1 factorial, x to the n plus 1. I'm going to be dividing, I know that. N factorial, x to the n. Now we got a new one here. You might say, oh, that's 1. We just did it. No, we didn't. We did n plus 1 over n. This is n plus 1 factorial over n factorial. This is a different animal. But I do know this happens. Now let's think about this. If this was 7, 7 plus 1 is 8 factorial. That'd be 7 factorial. We'll be left with 8. So whatever n is, that's what we're left with. Oh, that's it. So n times x. Phooey. N plus 1 times x. Sorry about that. So n plus 1 times x has to be less than 0. What did I say I do? I always forget this. But wait, n's going to infinity. The only time it's going to work is when x equals 0. So we would say x equals 0, and the radius is 0. This only works when x is 0. And by the way, if you haven't gotten lost, like, what only works? I don't even know what we're doing anymore. Yeah, exactly. We're going to crawl deep inside the belly of this beast, and we're going to come out the other side and not have any idea of what happened when we're inside it, but we're going to be able to do a bunch of weird math. So, hey, when does this converge? It converges to 0 when x is 0. Like, well, duh. Every term is 0 then. 0 plus 0 plus 0 plus 0 plus 0, duh. And the radius would be called 0. That's stupid. How could a radius be 0? Yeah, I know. Don't say I didn't warn you all beginning of this unit. So this is back to that negative thing. The ratio test is really a test for absolute convergence, right? It works to establish a radius convergence, as we just showed in a couple examples. We'll do a bunch more. Could be centered at A, could be centered at 0. The final thing that we need to resolve is the convergence at the endpoints. The radius is finite non-zero number. So that's very, very tricky. It's more of a next lesson unit, but yeah, we'll get to that. So determine the convergence or divergence of the series, blah, blah, blah. Well, let's do the nth test, just to be thorough. Let's put in 0. We get 1/2. And let's put in 1. We get 3/6, which is also 1/2. Let's put in 2. 9/25, 26, tending to 0. Right, no question about it. So keep going. Let's try the ratio test then. By the way, if you look at this, it's ignore the 1, because when you get freakishly big, it will be ignored. It's 3/5. It's a more or less a geometric series with a ratio of 3/5. So yeah, it'll converge. Let's do ratio test. Limit as n goes to infinity. 3 to the n plus 1 over 5 to the n plus 1 times plus 1. By the way, there's no x in here. What is going? Yeah, we do that. Times 5 to the n plus 1 over 3 to the n plus 1 to the n. Okay, I know this happens because these two are on top of each other. Left with 3. And in the long run, the 1 becomes irrelevant. We're left with 5. Yeah, I suppose I should show that. Nah, that bothers me. I'm going to do one more step. Limit as n approaches infinity of 5n plus 1 over 5 to the n plus 1 times 3. And so this is annoying to people, you know, when we get freakishly large, we can ignore the 1, just end up with a 5 on the bottom. End up with 3/5. 3/5 is less than 1, converges. Yeah, but what about the radius of convergence? There's no x in here, so we don't get into that. Yeah, but I don't understand. Why do we have n's and x's and then there's n's all of a sudden? Yeah. Yeah. How about a telescoping series? What do we call it that? Watch. So let's do our little fun here. 1 over n plus 1 equals a over n plus b over n plus 1 multiplied by everything. 1 equals a n plus 1 plus b times n equals 0. A equals 1. N equals -1. B equals -1. So we can rewrite it as sum n equals 1 to infinity. 1 over n plus 1, -1 over n plus 1. Well, let's write the terms. Put in 1. We get 1 over 1 plus -1/2 plus, put in 2, 1/2 plus -1/3 plus 1/3 plus -1/4 plus 1/4 plus -1/5. So on and so on. Well, these cancel, these cancel, these cancel, and these, it's all going to cancel. We're left with 1. So sorry, I just did that. Try not to. These cancel, these cancel, these cancel, these cancel. We're left with 1. Yeah, in case you thought you might want to try and do this unit without practicing, yeah, think again. This is just no bueno. A lot of work to do. Good luck.